ladies and gentlemen. We're going to do 5.2 today. We're going to evaluate and graph polynomial functions. Our objectives are to evaluate and graph polynomial functions, something other than quadratics, since we've been doing quadratics for forever. And then we're going to learn a new way to evaluate a function at a specific value. I want to remind you that you need a grapher. All right, you're going to need to have a grapher that you can take home. So you need to somehow procure yourself a grapher. Alrighty, so the first thing that I'm going to give you is a definition. Guess I spelled it wrong, I-T-I-O-N. Alright, there's our definition. And we're going to actually define what a polynomial function is. And we're going to define it in math terms. So it's going to look really ugly. And then we'll break that down and describe it in real people terms. So if I have a polynomial function, it will look like this. A sub n times x to the n plus a to the n minus 1, x to the n minus 1 plus dot 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 all the way down to a to the 1, x to the 1, and then a to the 0. All right? So that's the math notation. And it makes it look really scary, but it actually is not. An example of something that looks a little bit less scary would be something like 2x to the 4th plus 3x to the 3rd minus 5x squared plus 6x and then minus 15. Both of those things are examples of a polynomial function. All right? The a sub n is going to be important because that's going to be called our leading coefficient. Okay, this is my, and the negative goes with it, I just missed. This is my a sub 0, which is the constant, and if you will remember, that's also the y-intercept. Okay, notice that my terms are written with the highest degree on the left, and then they descend, meaning they get smaller. So I have 4th power, 3rd power, 2nd power, 1st power, and technically the negative 15 is x to the 0 because if you'll remember, anything raised to the 0 power is 1. All right, so that is what a polynomial function is. So I'm going to list some characteristics for you of those polynomial functions. All right, the first would be that in standard form, the highest degree goes on the left, and then they descend in order. Descend by degree. Okay? And again, if you look at the example that I gave you, the 4th power, the 3rd power, the 2nd power, 1st power, 0 power. So that's what I mean by they descend by degree. Okay? All right, so that's what our standard form looks like. Number 2 is that poly means many. Okay? So a polynomial is an expression that has many terms. Whew, a lot of writing at the beginning today. Okay, so a polynomial is an expression that has many terms. All right. The third one that I would tell you is that the exponents have to be positive integers. Oops. Oh, that didn't spell it wrong. Okay, so it has to be a positive integer. So that means no negatives for the exponents. It's okay to have a coefficient that's negative. So no negative exponents and no fraction exponents. All right. The next characteristic is just that your a sub n is called the leading coefficient. And that tells us lots of things, just like it did when we managed our quadratics. But primarily, I'm going to be looking at whether it is positive or negative. So that's what my leading coefficient does. And then the next characteristic is that a sub 0 is the constant, and that is your y-intercept. Okay, so that's always kind of handy. Let me flip my page. All right. The next one is that the degree of the polynomial is actually determined by the highest exponent. So if you think back to that example that I gave you at the beginning of our notes, it said f of x is equal to 2x to the fourth plus dot dot dot. Then this particular polynomial would be a fourth degree polynomial. And that also means that it's going to have 4 x-intercepts or solutions. We'll qualify that statement later, but for right now we'll just say that it has 4 x-intercepts or solutions. Okay? All right. The degree is going to determine, take out that, determines the shape. Okay? And I'll give you an example of this in a little bit, but for right now I'm just going to tell you that the degree determines the shape of the curve. And a straight line is still considered a curve, so it doesn't necessarily mean that it always has to be curvy. All right? So now let me show you just some additional information about several polynomials. So let's say I have f of x is equal to a to the 0, which means it's equal to a constant. Okay? The graph of this could be an example like maybe f of x is equal to 3, and that would be a horizontal line. Okay? So the graph of that, so if I had a little graph, there's my x and y coordinate, and this would be my graph at y is equal to 3. So we'll put a little 3 right there. All right, so that's what f of x is equal to a to the 0 would look like. All right, then if I had f of x is equal to a leading coefficient, and there's my x, and then plus a sub 0, notice that the degree on the x is 1, and this is going to be a line. Okay? So if I have anything that's to the first degree, I know that that's going to be a line. So if I had f of x is equal to 3x minus 4, then I know that this would be an oblique line. It would have a y-intercept of a negative 4, and then it would have a slope of 3. So my graph would look very basically something like that. All right? Then if I have f of x is equal to a to the second x squared plus a to the 1 x plus a sub 0, and again, that's just our official math language, I know that this looks like a parabola. Okay? And a real example of that might be f of x is equal to 3x squared plus 2x plus 6. And we've done tons of things with parabolas. There's my y-intercept, and I'm just going to draw a graph. I have no idea what it looks like, but we'll just pretend that's what it looks like. The point being that it's a parabola, so I went from no degree, first degree, second degree. So then if I went to a third degree polynomial, so a to the 3, x to the third, a to the second, x to the second, plus a to the first x to the first plus a to the 0. Whew! This is going to be a cubic function. All right. An example of that might be f of x is equal to x cubed minus x squared plus 3x plus 2. And again, I'm not actually going to graph this, but in general, a cubic function might look something like this. Okay? So that would be my cubic function. All right, and again, it's not necessarily the graph of this, that's just kind of an example. And then if I had a fourth degree, so this would be a to the 4, x to the 4, a to the third, x to the third, a to the second, x to the second, a to the 1, x to the 1, plus my constant. We call this a quartic, R-T-I-C, function. And basically, it looks like a glorified parabola, okay? So it might look like something like this, okay? And notice that it kind of looks like a parabola on the outside edge, all right? So those are just examples to show you what the degree does to the equation. So if I can go back and review, all right, if I have a 0 degree, no variable, it's just a straight line. First degree, I get a line. Second degree, I get a parabola. Third degree, I get the cubic function. And then fourth degree, it can look like all kinds of different things. It doesn't even have to have the W in the middle. Another quartic function could look something like a parabola and then kind of goes up that way. So what we're really focusing on is this outside behavior. The inside stuff we'll talk about later. All right, so I want to do a couple of examples. The first example, it says decide whether, lovely word, whether, a polynomial oh, sorry, I forgot a word, whether a function is a polynomial. Okay, I'm going to want you to write it in standard form. And then I'm going to want you to tell me what the degree is, what the type is, and what is the leading coefficient. So just lots of pieces of information about a particular function. So for our first example, we'll do h of x is equal to x to the 4th minus 1/4 x squared plus 3. All right, so if we talk about this one, notice that my degrees are all integers. Okay, I have a 4th degree, a 2nd degree, and a 0 degree. So this is actually a polynomial. It's already in standard form because the highest degree is on the left, the constant's on the right. Okay, the degree is determined by the highest degree term, so my degree is going to be 4. Okay, so it is a quartic, okay, which is the type. And then the leading coefficient, so my leading coefficient is going to be 1. All right, so that is our first example. All right, let's do another one. Let's say this time I have f of x is equal to 5x squared plus 3x to the negative 1 and then minus x. Well, the first thing you should notice about this one is that I have a negative exponent. So therefore, this is not a polynomial. Okay? Ha! I can't spell today to save my soul. Polynomial. There we go. Not a polynomial. Okay? And the reason that it's not is because it has a negative exponent. So then my next example, I'm going to have g of x is equal to 7x minus radical 3 plus pi x squared. All right, so if we assess this one, you'll notice that both of my exponents are integers. So this one is in fact a polynomial. It's not in standard form, so I need to rewrite it. So I would rewrite it as pi x squared, that's my highest degree, plus 7x and then minus radical 3. The degree is going to be 2. It is a parabola, okay, because a second degree is a parabola, and my leading coefficient, which is a little bit weird, but remember it's just a number, is pi. So my leading coefficient is pi. All right, so the next item that we're going to do is going to be evaluate. And evaluate always means get a value, okay, using direct substitution. And we've actually done this already, but maybe we haven't called it direct substitution. So I'm going to be given a function. So here's my first example of this. And I'm going to know that f of x is equal to 2x to the fourth minus 5x cubed minus 4x plus 8. And I want to evaluate it when x is equal to 3. All right. So to do that, and we've done this before, I'm just going to substitute 3 in for every place where there's an x. So it's going to be 2 times 3 to the fourth minus 5 times 3 to the third minus 4 times 3 plus 8. Okay? And if you do this math in your grapher, you should do it all in one step. Do not do it in little pieces. You will get 23. Okay, and you can check that on your calculator because I know you know how to do that. So then if I do another example, same idea, g of x is going to equal x to the third minus 5x squared plus 6x plus 1, and I want to evaluate it when x is 4. Okay, so that means I'm going to substitute that 4 in for everywhere there's an x. So this would be 4 cubed minus 5 times 4 squared plus 6 times 4 plus 1. And again, I would do it in my calculator, and I would do it all in one step. And when I did this, I would get 9. All right? And so that would be the answer on that one. So those are fairly straightforward. We've done those before. So now I'm going to teach you a cool new way. And I need to get I'm going to use two different colors on my pens so you can see what's going on. So this one's going to be called evaluate the function using synthetic substitution. We will use this process a little bit later again in the chapter for a different application, but this is kind of a fun way to do this, and it looks weird, but it's actually kind of an easy thing to learn. All right, so I'm going to do exactly the same problem that we did before using this new method called synthetic substitution. All right, so this is the key part of this one. So here was our function. We did 2x to the fourth minus 5x to the third minus 4x and then plus 8, and we evaluated it when x was equal to 3. So a couple of things about this particular method called synthetic substitution. The terms have to be in order, and by being in order I mean that the highest exponent needs to be on the left, okay? And I need to go in descending order. And then the next thing that's important is I need to put in a placeholder. I will show you what that means in a minute. Put in a placeholder if a term is missing. Okay? And then what I'm going to do is use only the coefficients. And a coefficient is that number in front of the variable. So first let's talk about, my terms are already in order, but I do need to find my placeholder, and here's what I mean. Here's my 2x to the fourth. My next term is a cubed term, but I'm missing the squared term, so I'm going to put in a 0x squared. Here's my 4x to the 1, and I just put the 1 so you see what I'm talking about. All right. If I go in order and I'm missing one of the degrees, I have to put in a placeholder, and I'm always going to put in a 0. So now I'm going to do the process called synthetic substitution, and I'm actually going to do a couple of examples for you, so don't worry if it seems a little confusing on the first one. I think by the time I do my examples, you'll be good. So the first thing I do is I write down what I want to evaluate it at, and I put it in that little weird little box. And then I'm going to write down my coefficients in order. So I had a 2, a -5, a 0, a -4, and an 8. I'm going to draw a line. You need to do this part. And I'm going to bring down the first term. Okay? So let me talk about what I've done so far. The first thing that I did was I put them in order. I put in my placeholder. You have to do that or it will not work out correctly. I put what I'm going to evaluate the function at in my little funny box. I wrote down all of the coefficients, drew a line, brought down the first term. So now's when I'm going to use my two different color pens so you can kind of see what I'm doing. I'm going to multiply the 3 times the 2, and I'm going to write it right there. So 3 times 2 is 6, and then I'm going to add. So 6 minus 5 is 1. Okay? Now I'm going to multiply the 3 times the 1, and I'm going to write it right there. And then I'm going to add. 3 plus 0 is 3. Okay? Then I'm going to multiply the 3 times the 3, and I'm going to write it down there, and I get a 9. 9 minus 4 is 5. And then I'm going to multiply the 3 times the 5, and I'm going to write it down right here, 15. 15 plus 8 is 23, and that is your answer. Yes, I know this is a lot of work to evaluate a function, but this is going to have a purpose later. So I would say f of 3 is equal to 23, and then I'm done. So it's really a cool process. We will use it for another method later, but for right now, this is all we're going to tell you about it so that I don't confuse you. So let's do another example of the same process. And again, this is called synthetic substitution. So I want to evaluate, okay, and I'm going to have f of x is equal to 5x cubed plus 3x squared minus x plus 7, and I want to evaluate it when x is equal to 2. And I'm going to evaluate it using my synthetic, gosh, I can't spell today, synthetic substitution. Okay? All right, so the first thing you have to do is look and see if I have any terms missing. This goes to the third power, second power, first power, 0, so I do not need any placeholders. So I'm going to put my 2 in, and then I'm going to write down my coefficients. 5, 3, -1, 7. I'm going to draw my line, and I'm going to bring down the first term. Okay? Then I'm going to start my process. 2 times 5 is 10. Write it down there. 10 plus 3 is 13. 13 times 2 is 26. Subtract 1, and I get 25. Okay? 2 times 25 is 50. Oops, write it down. And then 50 plus 7 is 57. So f of 2 is equal to 57. And again, it's that last number in what we've done. Kind of a fun way to evaluate a function. All right, I'm going to do one more just to make sure that we understand the process. So here's my f of x, and it's going to be equal to a -2x to the fourth minus x to the third plus 4x minus 5, and I want to evaluate it when x is a negative 1. So what you'll notice when we look at this one, my exponents go 4, 3, I'm missing the 2, 1, and 0, so I need to add that. And I'm just going to rewrite it here to make sure that we don't leave it out. Minus x cubed plus 0x squared plus 4x minus 5. Okay, I'm going to evaluate this one at a negative 1, write it down. Write down my coefficients, negative 2, negative 1, 0, 4, negative 5, and draw my line. Ooh, I'm running out of space. Okay, and bring down my first term, negative 2. So now I start my process. Negative 2 times a negative 1 is a positive 2. 2 minus 1 is 1. A negative 1 times a positive 1 is a negative 1. Add negative 1. A negative 1 times a negative 1 is a positive 1. 4 plus 1 is 5. And 5 times a negative 1 is a negative 5. A negative 5 and a negative 5 is a negative 10. All right, I'm going to circle that. And then I know that f of a negative 1 was equal to a negative 10. So it's really kind of a fun process. Again, we will use this later for a different application. All right, almost done. Just a little bit more to go. All right, so the next thing that I want to talk about is end behavior. And again, this is a new topic. You've never done this before. It's kind of a cool idea. And I want to talk about it when I talk about our parabolas that we spent a million years working with. So let's say I was given a function x squared plus 2x minus 3. Okay? I could factor this guy and I would get x plus 3 and x minus 1, and I could graph my little parabola because I know my x-intercepts would be 1 and a negative 3. So this would be 1. This is 1, 2, 3, my negative 3. So those are my two x-intercepts. And then my y-intercept is a negative 3. So my graph might look something like that. Okay? So what I want to talk about with end behavior is what happens to this graph at its extreme outside edges. Okay? So I really don't care what goes on in the middle. I only want to talk about what happens on its ends. Okay? And so the way that I would talk about this particular graph's end behavior, as the x values become more and more negative, my y values become more and more positive. And so I would say that the end behavior is up on the left-hand side. And then as my x values become more and more positive, my y values are becoming more and more positive, and they are also going up. So the end behavior for this particular graph is up and up. So that's kind of cool. All right. So the end behavior is what happens at the extreme ends, maybe I'll say edges of our graph. Okay. And gosh, I can't spell, sorry. It's kind of funny. I'm only interested in what happens on the outside edges. The graph could do all kinds of cool things in here, and I really don't care, because all I want to talk about is what happens on its outside edges. So let's say I have a different function, and I have one that is a negative x cubed plus x squared plus 3x minus 3. And we haven't talked about graphing these yet, so I'm going to bring in my trusty dusty calculator. I'm going to clear what's there, and I'm going to put in my equation. So I have a negative x cubed plus x squared plus 3x minus 3, and I'm going to do a zoom 6. Okay? And that graph looks pretty cool. All right, so I'm going to scoot my grapher over here. I know it's a little dark. And I'm going to draw a sketch of my graph. It doesn't have to be beautiful, but it does have to show kind of what happens on my graph. So mine's not exactly like this one, but it's close. So now let's talk about what happens on the outside edges. Over here on the left-hand side, my graph is going up. And way over on the right-hand side of the graph, we have to assume that it doesn't change, okay, then it would be down. So I would say that this particular graph has an end behavior of up on the left, down on the right, okay? Alrighty, so let's do one more example. I'll bring my grapher back in a minute. And let's say this one was x to the fourth minus x to the third minus 4x squared plus 4. And again, because we really haven't talked about how to do a graph, I'm going to do this one on my grapher, okay? So if I enter that equation into my grapher, x to the fourth minus x to the third minus 4x squared plus 4, and I graph it. I didn't do a zoom 6 because I'd just done that. Well, that's a cool looking graph. So I'm going to sketch a little picture of it, and I will always want you to sketch a picture of the graph that you use to solve a problem. See if I can get it out of the glare. And this graph is going to look like this, okay? And again, it doesn't have to be 100% accurate because this is just for me to know that you know what it actually looks like. So now let's talk about our end behavior, and I'm going to talk about what happens on that edge and what happens on that edge. Even though this is cool stuff in the middle, don't care because we're not going to talk about that middle part yet. So if I'm on my left-hand side, my end behavior is going up, and on my right-hand side, that is also going up. So my end behavior for this particular graph is up and up. All right, so now I'm actually going to come back to this graph, the very first one, and I'm going to show you some different notation. So I'll use my other pen so you can see. We write our notation differently. This is little kid math, so now we want to do big kid math. So here's the way I'm going to write it for right now, and we'll change it a little bit later, but for right now this is what we're going to do. I would say as x approaches negative infinity. That means as my x values get more and more negative, I want to know what the y values are doing. Well, we already determined that they go up, and up means positive infinity. So this is the same thing as saying it's up on the left-hand side. I would say as x approaches or becomes more negative, the y values are always going to be positive. So then let's go to the other side of the graph, okay? As the x values become more positive, as they go forever out this way, then my y values are also going up. This is the same thing as my up and up, okay? So this will be the notation that we will use for a little while. We will change it slightly later, but not right now. So then let's talk about this graph. As my x values become more and more negative, as my x values go to the left, the y values, which is what f of x represents, are going to be positive. We said it was up. This says that it's also up, okay? And then if I go to the positive side, up as x approaches positive infinity, notice that my y values are going down, and I would say they approach negative infinity, okay? Kind of cool. Big kid math. So now let's go back and do the last example. Okay, as my x values go more and more negative, my y values are going to approach positive infinity, which also says up. And as my x values approach positive infinity, my y values are also going up positive infinity, okay? This is the notation that I will expect you to use when we talk about end behavior, all right? If it's helpful, you could show your little arrows first, but then you need to translate that into big kid math, all right? Okay, the last thing that I'm going to do is kind of condense some of this information and talk about graphs in general, all right? So let's say I have an equation and the degree is odd, like 1, 3, 5, something like that. And my leading coefficient is going to be positive. Okay? Then what that means then is that the graph very, very generally might look something like that. Okay? Alrighty. And here would be my end behavior. And I'm going to write it two different ways. Okay? Gosh, I can't spell today. So sorry. B-E-H. There we go. Now we're all going in the right direction. So notice that my end behavior on the left is down and my behavior on the right is up. And then I'm going to write it in my new notation. As x approaches negative infinity, my y values are going down. And as my x approaches positive infinity, my y values are also approaching positive infinity. Okay? This and this say the same thing. All right, so now let's say my degree is still odd, but my leading coefficient now is negative. So it creates a reflection in the graph. So my graph would now do something like this. Okay, so it would go the opposite direction. So now let's talk about that graph's end behavior. And again, remember, it doesn't matter what's going on in the middle portion of the graph. All we're really talking about is out here. That's why the value of the degree is irrelevant. All I want to talk about is if it's odd or even. So in this particular graph, my end behavior is going up and down. So now let's write it in big kid math. I would say as the x values become more and more negative, my y values are going up. And as x approaches positive infinity, my y values are going down. Okay? Alrighty. I have two more of these. Okay, because we talked about the odd exponents. Let me get a different sheet of paper. Now we need to talk about the even exponents. Okay, and I'm just about done. I just need to finish this, and then I'll give you your problems. All right, so then let's talk about what happens if I have an even degree and my leading coefficient is positive. Okay. In general, regardless of what happens in the middle, it could look something like this. Okay? Alrighty. Really doesn't matter what happens in the middle. So then my end behavior is going to be up and up. Okay, a parabola is a good example of this. So now let's do it in big kid notation. As x approaches negative infinity, the y values are also approaching positive infinity. And as x approaches positive infinity, my y values are also approaching positive infinity. Up and up, up and up. Last one. So if my degree is even and my leading coefficient is negative, okay, then it's going to be a reflection of that graph, which means it's going to flip, and it could look something like that. Okay, so now let's talk about that in behavior. So this graph's end behavior is going to be down and down. Okay, big kid math. As x approaches negative infinity, the y values are also approaching negative infinity. And as x approaches positive infinity, my y values are also approaching negative infinity. Okay? So that's very cool. All right. Now let me give you your problems for the day. I have a few words to write for the directions of each, so sorry, that's a little long. The first one says, decide whether, lovely word again, whether, the function is a polynomial. Okay. Then I want you to put it in standard form. Okay. And then I want to know what the degree is. So state the degree. I want to know the type and the leading coefficient. Alrighty. Two of these. First one is h of x is equal to x times the cube root of 10 plus 5x to the negative 2 plus 1. Okay. My second one, b, is going to be h of x is equal to 8x cubed plus radical 2x minus 4x squared. All right. Your second problem says use direct substitution, which is the kind that you like to do or that we've done in the past. It's not the new method. Okay. To evaluate. Okay. And you're going to have f of x is equal to 6x cubed minus 25x plus 20, and I want to evaluate it at x is equal to 5. Okay? All right, and that's an x. Sorry, bad handwriting. Okay, your next problem, problem number 3, says use synthetic substitution to evaluate all right. You need to be careful and remember to think about your placeholders. The first one is f of x is equal to 8x to the 4th plus 12x cubed plus 6x squared minus 5x plus 9. And I want to evaluate it at x is equal to a negative 2. And then your second one is going to say f of x is equal to a negative 8x cubed plus 14x minus 35. Remember again not to forget your placeholders and evaluate it at x is equal to 4. All right, one more problem. Okay. It says sketch, that's a C, the graph using your grapher. So remember, you have to show me a picture of your graph, otherwise I ding you for not showing your work. And then I want you to describe the end behavior. And I want you to use what I was calling big kid math. Okay, so remember to use that notation. All right, you have two of these. So the a, f of x, is equal to a negative 2x cubed plus 7x minus 4. So you'll put that into your grapher and then describe the end behavior using the big kid math. Okay, that is our cool new notation. The second one says g of x is equal to x to the 4th plus 3x cubed minus x plus 1. Alrighty? And those are the two that you're going to put in your grapher and then describe the end behavior. Alright, well done. Good luck with the problems, and I will see you tomorrow.